Thank you very much, and thank you for being here. I guess the rain stopped. It should not rain in Southern California, I thought. Anyway, so so what I'm going to talk about is solid-liquid interfaces, and you've seen variation of this kind of, pictures where they're important in various flavors. So that's my pick showing some of the things we're interested in particular corrosion. But while most of this, the effects that we see from these reactions are seen on the macroscopic scale, everything is starting at the microscopic scale, and you've also seen various flavors of, how this interface looks like. And what happens when a metal comes into contact, let's say, with an aqueous environment is the same what happens when you have two different condensed phases coming in together, which have different electronic structure, and you have to have some kind of equilibration here in order to align Fermi energies, and this is what leads then to the formation of the double layer. And of course, there are also chemical reactions, because we know that metals are not the most thermodynamically stable phase in most cases when we are in an electrochemical environment. So we have, the electrostatic potential is of course related to the double layer, but we have then formation of oxides or other kind of structures that appear there. And we have also heard over the last days that interfacial water is different and has different properties, how it orders ions and so on. So what we would like to look at is, how these reactions that are going on here, which is basically making and breaking of bonds, how they are influenced by these different properties of interfacial water and the electrostatic drop. And the challenges we are facing is, how do we look at something which looks, even in this cartoony thing, rather complicated given the cells that we are having in ab-initio or atomistic calculations, which are a few hundred atoms, containing just a few hundred atoms. And so how do we translate such a material's complexity into something that we can calculate, and how do we account for the environmental conditions, which in this system will be pH and electrode potential, which govern and influence significantly what is going on. And what I would like to talk about is about how to get electric fields in these calculations, because this is, we have an electric field that we have there, a potential drop into interface, but we need also to get it into something that is kind of shown here, which will be a typical DFT supercell. And how do we handle potential fluctuations? Because what experimentalists do, they can change the potential, they can have a constant potential conditions, and they can then basically, they have like a joystick, like changing temperature and pressure in the gas phase. Here, we can change they can change electrode potential. And so, if we want to be realistic, we need also to be able to reproduce these things. And the systems that I will be talking about, focusing about, are platinum water interfaces with hydrogens, and then hopefully I also get to talk about magnesium corrosion. And most of the work that I will be presenting was done by two PhD students, Sudarshan Surendralal and Florian Dijsselbeck, who were really very clever in helping us develop all these approaches. So, why platinum? That's kind of the fruit fly in electrochemistry, I would say, one of the most studied systems, which of course for theorists is also very good because we can compare to experiments. And it also has industrial relevance. And what is also nice, so here is a cyclic voltammogram, which shows you how the current changes as you change the electrode potential. And what you can see that it is really reversible whether you go in one or the other direction. So we are in a thermodynamic regime, and so we don't have to worry about kinetics. And what we are interested in is this regime here, where we have hydrogen adsorption or hydrogen desorption, and here a region where the platinum surface would be pristine. Now, what's interesting about this system, that there seems to be a maximum coverage that can be reached, which is about 0.66 monolayer of hydrogen on the surface. And this is different from vacuum, where one could go to 1 monolayer coverage. And so we wanted to understand a little bit better the interactions that are going on. And so we looked at hydrogen absorption on platinum, the platinum surface. And here you can see, so this is a top view of our computational cell. And here you can see what the unit cell would look like with the various high symmetry adsorption sites that you would have. So two hollow sites, a bridge site, and also a top site. We did VASP calculations and performed molecular dynamics calculations. And what you see here is basically the same kind of structure, but this is then now showing DMD trajectories. And you can see that the platinum atoms of the first and the second layer are kind of vibrating around the equilibrium position, while the hydrogens are having a kind of spanning a somewhat broader space, which looks a little bit different. Here it's more symmetric on the top side. Here it is more asymmetric. And this is for a particular coverage I'm showing. Now, having this trajectory is what we can do is that we get the probability distribution for the hydrogen. So basically the lateral, we look at the lateral positions of the hydrogen, which we can calculate. And this is kind of the plot that we get. And so here I have indicated the various high symmetry adsorption sites. We can have the bridge site, top site, and the hollow sites. And having this probability distribution, I should mention also that we exploited surface symmetries in order to boost the convergence, so that we actually, even from somewhat moderate lengths of the trajectories, we can get a rather smooth potential energy surface. We can calculate using a Boltzmann inverse the free energies. Now, why is it interesting to understand where the hydrogen is located on the surface? It is assumed that the hydrogen evolution reaction is going when the hydrogen is in a top site, so sitting on top of a platinum atom of the surface. If you do t equals 0 calculation, the hydrogen is mostly sitting in a hollow site. So there is a certain interest in understanding how and how often does the hydrogen go to the top site. Does it go at all or not? And so having such a free energy profile, the free energy potential energy surface, we can exactly exploit this. Now, what we see here is that we have kind of an extended basin that is related to the FCC hollow site, which also encompasses the bridge site. The HCP hollow site is not really a stable site, so here you can see a cut to this profile. So you see that the FCC bridge site is kind of having the lowest base in the HCP site is hardly there, and the bridge site is somewhere in between. And there seems to be a second basin which is much more symmetric, which is associated with the top adsorption site. And that if you increase the temperature and go to room temperature, there is also a certain probability of occupying the top sites, and there is probably the most likely path is going kind of this way, but via the bridge, but we haven't explored this now in details. But you can also see we don't have here an absolute barrier, but we have a relative barrier when we go from the one hollow site to the other hollow site, and that's a free energy barrier. What was interesting, we did this calculation both in the presence and in the absence of water. So we have the surface in vacuum with hydrogen and the surface with liquid in hydrogen. And these are the free energy surfaces which are calculated for vacuum, and this is when we are solvating the surface. And what we found astonishing at the time, that they are extremely similar. So it is like water is not there. I mean, there are small differences if you look here at the profiles, but I would say within our resolution, I would consider this to be degenerate. Probably if we have machine learning potential as something where we can really go to much longer time scale so that we get better statistics, then I will be more confident in the errors. But for our purpose at the moment, it seems that there is really no difference between vacuum and solvation. So this is probably because the hydrogen is interacting stronger with the surface, but also when you consider hydrogen, you would expect that it forms hydrogen bonds to the water, so it's not obvious that this would have been the case. So then is water only the spectator? Do we need it? Can we neglect it? So for this, one needs to look, what the role of water is with another property. And what we focus on is here the work function. And so the work function can be equated to the electrode potential. They're certainly related. And we look then how the work function, so this is the energy that I need to move an electron through the surface and kind of bring it in the vacuum. And of course, it needs to be taken from the Fermi energy, but it also needs to overcome the surface dipole that is present at the surface. And when we do calculations for vacuum, and I aligned here at the work function of pristine platinum, we see that we have kind of a decrease in the work function as we increase the hydrogen coverage. And not very astonishingly, this is very close to what we know from experiment. And we know that we can typically kind of describe this property very good using density functional theory, even with standard functionals. Now, what happens when we put water in there? These are now experimental results that we have taken. We see that there is a shift with respect to the curve that we get in vacuum. But if we basically backshift these experimental values, they seem to be lying pretty much on what we have in the vacuum situation. The difference is, of course, that at some point, this is stopping. And so trying to understand this, we look, what the system is doing and how it is building the double layer. So what would happen is, of course, that initially, I should mention we also performed an explicit DFT calculation where we have the surface in contact with water. And so you can see the point that we have calculated. And they seem to follow very well the experimental result. And we seem to have here kind of around this 0.6 coverage, we seem to have a change in behavior. So here we have kind of a downward slope. Here we are going upwards, and we are at one monolayer, basically recovering the value that we are having in vacuum. Now, trying to understand this, again, we look how this work function or electrode potential changes as we increase the coverage and what are kind of the underlying physical mechanisms that lead to this. So first, when we bring water in contact with the platinum, there will be, because we have different electronic structures, different surface dipoles, there will be kind of a rearrangement of the water molecules trying to screen the potential drop that we are having here. And basically, this is the shift what leads to the shift when we have the pristine surface. If we were to change the electrode potential and put some charge on the platinum surface by changing the potential, what would then happen is that by absorption of hydrogens or any kind of other ions on the surface, there will be a certain amount that needs to be absorbed in order to screen the charge that we have on the electrode potential. And this would lead then to this kind of change in the electrode potential, so it will shift the curve down. If we keep increasing the potential, this would lead to a higher absorption of hydrogen on the surface that would try to screen the surface dipole, so the kind of the potential drop that we have in the interface. And this seems to be working up to a certain point. And then further increasing the hydrogen coverage, will not counteract increasing the bias potential. What can a system do in such a case? It will gain electrostatic energy by creating a dipole. So what it can do is it would, desorb a hydrogen for the surface, forming a hydronium ion close to the surface, and then this would allow to screen kind of higher potential drop. And this is also what we see in our calculation. So if we run this one monolayer coverage calculation, so we have one monolayer hydrogen on the surface in water, we run an MD simulation, and after around 20 picoseconds, we do see that there is a hydrogen desorption event. We form a hydronium ion, which resides close to the surface, but in this way, it has created a surface dipole, and it can screen the potential drop that is there at the surface. And this is also, how you can imagine, let's say, that a double layer forms. You have a rearrangement of the ions. Katerina was discussing, how ions would order, and now we've also seen it in talks of Axel and so on, that you have a rearrangement of positive and negative ions close to the interface, which basically try to screen the potential drop. And why this is mostly on the water side, because on the other side, if we have a metal has infinite screening, so you have some charge maybe on the first layer, but then afterwards it's like a wall, and so most of the changes are on the aqueous side. If we have a semiconductor or an oxide, then the relationship will be more complicated because the screening on the oxide, so also on the solid side, is kind of less than infinity. And so you may have a much more complicated relation with respect to how the potential drop is on both sides. Now, trying to understand this behavior, in a computer, you can do a lot of things, and you can kind of subdivide your work function into different contributions. And we did so, subdividing in 3 contributions. One, which is related to the adsorption of hydrogens to the surface. And this is a contribution that one would have also in vacuum. Then there are 2 contributions that are related to water. So there is a certain amount of water molecules that are adsorbed on the surface, and they will transfer charge or electrons to the surface, so it certainly will interact. So they will give a certain contribution. And then there are the water molecules which are in the vicinity of the surface, which will then reorient in order to counteract a potential drop. And obviously, the 2 contributions that are related to water will be only present when the surface is in contact with water. Now, when we plot these 3 contributions, again, as a function of the coverage, then we can see that they have different behavior. And so let's first focus on the one that is related to the hydrogen here. If we put it kind of basically in the plot I was showing before, so we can see that it kind of very closely follows what we have when we have in vacuum. So this is really the contribution that is also present when we are in vacuum, and how the hydrogen interacts with the surface. What about the 2 water contributions? Now, one thing to notice is that when we kind of look at how much electron does a chemisorb water kind of transfer to the surface, it seems to be kind of a linear behavior, indicating that each water molecule contributes the same amount of electrons to the surface. What we also see that there is a correlation between the number of adsorbed waters and the adsorbed hydrogen. So the more hydrogen there is adsorbed on the surface, the kind of less water I have. So basically, as I adsorb more hydrogen, then the water leaves the surface. And eventually, when I have a full monolayer, we get to the situation Axel was describing, where the surface becomes hydrophobic and the water is kind of pushed up. And what is also interesting to notice, sorry, I was too fast. If we look here at the behavior of this contribution that comes from the electron transfer from water and the one which comes from the reorientation of the water molecules, up to maybe half a monolayer, they seem to be very similar, but in opposite directions. So to a large extent, they will cancel, but they will give a rise to a shift, which will downshift this curve. So if I go back to this situation, basically, this would explain why this curve and this curve are very similar, because up to this point, basically, the water contribution is only downshifting the hydrogen contribution, so this orange part. If we go, however, to coverages that are higher, then just by reorienting the water molecules, we can no longer counteract the loss of screening that comes by water molecules leaving the surface. And this is then where it is then not only just a downshift of this curve, but really we have a different behavior. So we have these 2 curves, then if we put them together, can no longer cancel each other, and so we get then this inversion in the behavior. So this is when we come to this kind of upward slope. And again, initially when we go to 1 monolayer coverage, because the water layer is initially pushed up, it is like the hydrogen-water platinum interface being connected a little bit to vacuum, initially it would seem that we are basically recovering the behavior that we have in vacuum. And of course, this cannot counteract the the potential drop, and then we have this desorption mechanism. Now, it's also interesting to look at adsorbed water molecule. So this is kind of a side view. This is the platinum that is sitting below a water molecule, and what you're seeing here is the difference electrons density, so basically what kind of orbitals are polarized. And the conventional picture that we have is that when a water molecule adsorbs on the surface, it will kind of transfer maybe charge or interact directly with the platinum atom on which it is sitting on a top side, and therefore they will form kind of a bond. But this is kind of localized to the position of the adsorbed water molecule. What we see, however, is something different. If you look here at the top view, now this is the water molecule, this is adsorbed on platinum, and it seems that this platinum-water complex that is formed, so it's like a molecular bond because both the platinum and the water seem to donate electrons to the surface, and they're donating it to the surrounding platinum molecule. So it is really, when we do the math, then kind of they really counteract. So each water molecule needs a bigger surface area in order to adsorb. So it will claim not only one atom, but it will claim an area of a few atoms. And this would also mean that we cannot reach a 1 molar coverage of water. We see something like a 2/3 coverage of water that we reach with these chemi-sorbed water molecules. And it is not like a static thing that the water is bound and not moving, but we do see exchange between the adsorbed, chemi-sorbed water and the first layer. So it's a dynamic equilibrium, I would say, but the maximum coverage that we seem to observe is 2/3 of a layer. And so then we start adsorbing hydrogen. Hydrogen, of course, would also interact with the platinum, and then platinum, they are competing basically for the same platinum atoms, and therefore eventually the hydrogen wins and is pushing more and more water molecules from the surface. That's very nice, but so far I was discussing the electrode potential. I didn't apply any electrode potential. I was doing something that we can do easily in physics. You know, we can adsorb something and then see what is the reaction. Experimentalists do something different. They have their system, they apply a potential, and then see how the system reacts to this applied potential. So in principle, the system I would like to describe is one in which I have electrodes immersed in water, and of course there is a potential drop. Now, we've discussed in various talks the potential drop, and we know that most of it is located very close to the interface, and then Katarina was describing yesterday also the various theories that we have to discuss it. What is nice is that far away from the interface, basically the potential is flat, so we are recovering the bulk values. What I'm interested in is, of course, describing this part. And so if one would go to a mesoscopic system, then one would probably reach to the region where also we are in the bulk region, so we are flat. But we have also this rapid change of the electrostatic potential at the surface here. Of course, my DFT cell will be much smaller, and so I will capture only this kind of small part here. And so the question is, how do I describe within this system something that will then correspond to this system and eventually to this system? So how do I get this? And this is what I would like to discuss in the next few slides. So mostly our target is to describe the inner and the outer Helmholtz layer and maybe part of the diffuse layer. But then we would also like that what we have on this side exactly replicates the potential dependence that I would get when I consider the overall system. Now, the first question that I have to ask is, how do I get charge in my system? Because I'm having periodic boundary conditions. So what are the requirements that I would have? I would like to kind of charge my working electrode here, and maybe I can do something like in experiments, so have kind of a reference electrode. However, I would stress this is a computational electrode for us. This is just kind of a means in order to charge the system. This is not something that you would really have in experiment. But of course, we have certain requirements to this reference electrode, because it should allow us, to electrify our electrodes. It must then accept and donate fractional charges, and I stress fractional because we have a small supercell, and if we want to be comparable in terms of the charge that we have on the surface to what is there in experiment, if I put a whole electron in my small supercell, I will be at much higher charges as compared to experiment. And we would like this reference electrode to be kind of a spectator, so not to perturb the system too much. So it should have ideally a small surface or interface dipole, be inert to adsorptions and reactions. So it's just, for me, a means to kind of charge my working electrode. And of course, if we need to control the potential, it should work with the potentiostat. Now, how do we achieve something like this? What we want, this is my working electrode, this is my computational reference electrode, and let's say they are a different, have different Fermi energy. So if I have a state occupied here, then I will have a charge transfer so that I have separation of charge, getting a negative and a positive charge, and this will induce then an electric field, and I will have a potential drop between the two electrodes. This is the situation I would like to have. The reality is that I have periodic boundary conditions, which means that, of course, this is repeated in all directions. And what I want to have is then, it's kind of mandatory that the potential that I have here is the same, the potential that I have here, which would mean if I don't do anything within this region, yes, I will have field in this direction. Here I will have exactly the opposite field. Thankfully, there is the dipole correction, which has been around for a very long time, developed by York, and this allows us to get in such a vacuum region a flat band potential, and this kind of potential drop is basically the difference between the interface dipoles that I have on both sides. There is a second difficulty that comes from having periodic boundary conditions, because at the end of our DFT self-consistent calculation cycles, the Fermi energy, we need to have one kind of Fermi energy throughout the system, which would mean that if I have on both sides a metal, there will be a charge transfer. I will shift my two Fermi energies, and I basically lose the potential drop. So that's not the situation I want to have. And then we thought, okay, why not take a semiconductor? Because then we do have a band gap. There is a forbidden region. And then if I P or N-type dope the semiconductor, then I would have charge transfer from the metal in one side or from the semiconductor to the metal in the other side. And by this, I will kind of create a field. However, finding a suitable semiconductor was not easy, because I have my two interfaces in the same cell, which means that I need to lattice match them, which means that most semiconductors, if I deform the lattice so that I ensure that my working electrode is not strained, my semiconductor electrode will be strained, and this will decrease typically the band gap. However, we needed to cut, so, and in a DFT, we generally underestimate the band gap with conventional functional. So for something, like gallium, I think we tried gallium nitride or so, which has a big band gap. It was then pushed down quite a lot. Okay, so what to find as a kind of a computational reference electrode? So what we wanted to have is a very large band gap, even for DFT calculations. Should have a small deformation potential so that the band gap is not reduced further when I try to lattice match the two electrodes. And again, be inert to possible reactions to the solvent. And what we came up, or Jörg Googled and found that neon is the crystal with the largest band gap in nature. Doesn't mean that we have to have, now a neon electrode in experiment, but for us that's convenient. So the band gap is 22 eV. Even with PBE DFT, it is like 11 eV, which is severely underestimated, but for our purposes, it is still big enough. And the nice thing about neon is that the band gap is an atomic property, not due to, the bonding between the atoms. So if I deform the neon, there is hardly any change in the band gap, so it remains as big as it wants. What is also important is we want that the bent edges of our computational electrode basically straddle the bent edges of water, so that I can hopefully go through the whole region of the band gap of water and vary my potential within this region. And so our setup that we conventionally use now for our calculation is that we have here a working electrode, which is basically a slab of a metal or semiconductor, doesn't matter what we want to do. And of course, this is periodically repeated. We do have here a neon counter electrode, which is just one layer, and it fulfills the purposes, and in between we have then water. Now, to do the charging of the neon, we use something that is known very much used in semiconductor physics. We employ pseudoatoms, and these are neutral objects which have one changes both the core and the valence charge in the same way. So the thing is neutral, and I change it by a fractional number. So if you have ever done semiconductor calculations, or read literature, you saturate typically the backside of the slab by one hydrogen with 3/4 or 1/2 or whatever, and these are exactly this kind of pseudoatoms. And we use rather small numbers here, and this is distributed over the neon layer so that we can not perturb too much the pseudo-potential of the neons, but nevertheless, this allows us to charge our working electrode. So what we have now achieved is that we can charge our cell and have a potential drop between the two electrodes, even when we are in a typical code where we have periodic boundary conditions. But what we would want now is to be able, both in a static and a dynamic calculation, to kind of have the correct potential. Now, I want to have, again, on this side, exactly what I have on the, in the real system. From here on, I will be obviously somewhat different, because here my value will be constant. It will exactly be the same as the one of the overall system, but I'm not worried really about this kind of difference in the potential, because this can be taken out by some kind of a posteriori correction, so some kind of embedding that we have there. But how exactly do we do the embedding, and how do we ensure that we have here the electrode potential that works with in a dynamic calculation or even in a static and reproduces what we want to have? And there are three different boundary conditions that we can impose, and this have been discussed in the literature. And again, if I'm in an infinite system, which I want to describe, these boundary conditions don't matter, because I have enough states to sample the overall system. But here I'm confining my system, and I really need to worry about how I do the embedding. Now, constant charge boundary conditions would mean that I put some kind of charge on my electrode, and throughout my calculation, this charge stays the same. So if I look at the distribution of the charge on the one electrode and on the other electrode, here I will have this surface charge. Here I will have kind of a distribution, a constant counter charge. And if I look now at the kind of reaction in which so here I have a plus, here I have a minus charge, and now I look at the reaction where I, for example, move one neutral atom from my surface into my water region. And like the reaction I was showing in the beginning, where we had kind of hydrogen going into solution as a hydronium, I have then here a positive charge, and it leaves its negative charge on the surface. Now, because we have the condition of constant charge, this extra electron cannot go away, so it will remain at the surface. And if I move my atom or ion now further away from the surface, I will create here a dipole. And because we have periodic images, there will be really an array of dipoles that are kind of in a lateral direction. It's an array of dipoles. And so this will have, of course, an influence on the potential that I have at the interface. So therefore, this would be suitable, if there are, to consider this condition, if I don't have any charge transfer reaction, so I have kind of an equilibrium situation where I don't change the charge. And so for computing equilibrium properties at zero charge, this will be a suitable boundary condition that will describe also what I have in the overall system. But of course, I never know a priori whether I won't have some kind of reaction which will change the situation. Now, what is the other boundary conditions that is also popular? This is the constant electric field boundary conditions. And this would mean that I have throughout my calculation always the same field. So if any kind of change happens, then I may have here a variation in the surface charge on the electrode and also on the counter electrode, but this must be such that I ensure that I have a constant field. If I look again at my kind of toy example in this reaction, then what will happen if I have an electron that comes here, this will be immediately kind of dissipated. There will be an electric current in order to ensure that I have the same field throughout the calculation. So even if I have a moving atom, I will always effectively discharge the double layer. And so this will be a situation where we would get a current, but of course, I cannot describe the system exactly. And in order to sample also this boundary condition and see that our kind of what we were thinking hypothetically is also true, we did a simulation where we had MD for 64 explicit water molecules, sandwiched in a supercell. This is comparable to a DFT calculation, even if we did the calculations on the level of TIP3P water. And then we looked what will be the distribution of the potential drop close to the interface and also in the aqueous region. And what we see if we are at the constant charge conditions, we see at the surface, at the electrode, we have really a constant charge, meaning a delta function. While when we are further away from the surface in the aqueous region, we have kind of a distribution like one would expect to have it. So in this condition, we can describe the interior of the electrolyte rather well, but when we go to the interface, this is not the case. Now, if we go to the constant field conditions, we see that we are close to the interface. We are kind of getting a distribution as one would expect, so we are describing the system well. But when we go to the interior of the electrolyte, actually the system is sampled and we don't get the distribution we would expect. Now, we need to have something in addition to this kind of two extreme cases of constant charge and constant electric field in order to be able to sample on one side here close to the interface this distribution and in the electrolyte this distribution, so the red and the blue. So get a new boundary conditions. And this is where the development of the thermopotentiostat come in, where Stefan and Florian were essential. Now let us look at our system. So we have a setup which is kind of reminiscent of a capacitor. We have charge on both sides. If I have a water molecule, and this is a molecule which has a dipole, and now there will be thermal fluctuations in the system when I do molecular dynamics simulation or even in a real system. So let's assume the water molecule changes direction. What will happen if the system is at a given potential? The potential will kind of react and will change. And in order to keep a constant potential, there has to be exchange of charge between the two electrodes. Now, if I don't ensure that now the charge is returned to the degrees of freedom from where it is taken from, but I just put the potentiostat, which returns the energy indiscriminately to all the particles that I have in the system, over time, I will cool my system. And this is eventually, I will get kind of flying ice cube effect. So I get the correlated motion between the water molecules, and they basically move out of my system like a bullet. So what we know, of course, is that there are fluctuations within the systems, and these fluctuations ensure that the dissipated energy is returned to the degrees of freedom from where it is taken from. So what we then used is the fluctuation dissipation theorem in order to derive, how the charge should propagate from one state to the step to the other, in order to ensure that we are returning the charge to the correct degrees of freedom. And so for this, Stefan used iter calculus in order to derive these rather simple-looking equations. And of course, here we've seen variations of this kind of term in various talks also, so where we have a Wiener stochastic process here. So far away from the equilibrium, the term, which is the dissipation term, will drive my system towards the potential that I want to have, so this P0. But once I'm close to the equilibrium, this kind of fluctuations will ensure that on average I get the potential that I want to have. And this has been implemented in VASP in LAMMPS, and I hope by the end of the year we have it also in the, generally available in VASP with the new Python bindings. So if we use now our thermopotentiostat, we can look at the distribution that we get. This is the green one, and we can see that both close to the interface and in the electrolyte region, we get kind of a distribution as like we would expect it. And so we ensure that we are sampling kind of the correct distribution. Now we can use this in order to really look at an example where the potential matters. And this is corrosion of magnesium. Magnesium is quite interesting because it is an extremely light and non-toxic material. So it's interesting both for structural application, but also if you think about medical applications, implants, and so on. One of the, I would say the major problem in particular with respect to corrosion, it is its low corrosion resistance. So if you look here at the galvanic series, magnesium is kind of the most corrosive element you can think of. What is very interesting about the magnesium under anodic conditions, so this means that the magnesium metal is actually positively charged, it's electron deficient, is that one sees a very violent hydrogen evolution reactions, like you can see here in this movie. Now, a hydrogen evolution reaction is one that is expected under cathodic conditions, so where there are excess electrons, because it's assumed that the reaction that leads to the formation of hydrogen consumes electrons. Now, if we are going to anodic conditions where we are electron deficient, this reaction is not expected to take place, so one would expect that the usual behavior will be hydrogen evolution drops. That's not the case, so one can see that experimentally, the curves show that there is an increase in hydrogen evolution. Also, if one looks at the amount of magnesium that is dissolved also during this reaction, which is enhanced, and the amount of electrons that, or the hydrogen that is found, one must need use a magnesium 1+ ion in order to explain the ratio. But from our even school chemistry, we know that magnesium is typically a 2+ ion, so that's kind of thing that can't be reconciled. Now, what we did is then to perform molecular dynamic calculations first, without having any potential control, and there was here what we see is that there is dissociation of water, so a certain amount of OH groups adsorbed then at the surface. There's also a certain amount of hydrogen that is set free by this dissociation process, which may stay at the surface or penetrate the slab. And what's plotted here is so the surface normal direction, and here is the evolvement of the system, the trajectories over time. And any kind of, just vibration of the water molecules or the magnesium atoms that are not very interesting, we have just blended out and shown here as kind of these blobs of yellow and blue. And only where some kind of event happens that is interesting, you see explicitly the trajectories for the OH or for the hydrogen. And what's interesting, when we don't apply any potential control, we reach a OH adsorption, which is corresponding to 1/3 monolayer. And that's the maximum coverage we reach, which is also consistent with what was found thermodynamically by other calculations. We don't see, however, any kind of reaction. Now, if we apply now potential control and polarize our system anodically, meaning that we are energy deficient, we do see reactions. As you can see here, this plot kind of has many more lines. And so all the water molecules that are not important, let's say, are blended out, and we only show here the one water molecule which kind of reacts with the hydrogen from the surface, and then there is a formation of a H2 molecule which eventually goes into solution. What we see that initially we have, again, dissociation events. We have also the formation of a hydronium that kind of goes to the other side in order to screen our potential within the cell. But we also see that we do have hydrogen evolution events. And so this is the first one that we see. When we look at the mechanism that is there, then we see that a water molecule picks up with the hydrogen, a hydrogen from the surface, and this leaves eventually forms the H2 and leaves the surface. Now, if you know, let's say your chemistry, most people know that the hydrogen on the water molecule is positively charged. And so why would a positively charged ion go to something which we also expect to be generally positive and pick it up? But this is due to the hydrogen on the surface actually being negatively charged because of the magnesium properties, which has a very big spill-out density. So the way that the reaction goes is that actually the adsorbed hydrogen is negatively charged, so it carries a negative charge. You don't need an explicit electron like here. And then this negatively charged hydrogen reacts with the water molecule, so then you have kind of a redistribution of the negative charge, which goes on the OH, and you form the H2. So it's kind of a modified Tcherovsky mechanism that we propose is important. This, however, doesn't explain now the magnesium 1+ ion. And I mentioned that this is the only one would kind of explain the ratio between H2 absorption and magnesium. So for this, we now did a calculation for a vicinal surface. So we do have a kink position here, so not a flat surface, but one that is imperfect. And one would expect that this kink atom would be the one to be the easiest to dissolve. And what we see that initially we do have kind of really, again, water dissociation, a certain amount of OH adsorbs on the surface, hydrogen is also on the surface. And then we come to a situation where we have a magnesium atom that is going into solution and anchored, however, to the surface by an OH ion. So this OH ion you can see maybe here. I don't know, it's not very clear. And then we were thinking the magnesium would go out. So we thought the rate limiting step is really making from a neutral magnesium atom, a magnesium 2+ ion, forming the solvation shell, and then the magnesium just goes out. That's not the case. So it is not this kind of electron transfer reaction that we would expect. That is the rate limiting step. But basically this OH glues the magnesium to the surface, and we try to drag it out in order to see how strong it is. I'm done here, yeah. And it's a binding energy of 2 eV. So it's really super stable, and it is happy. It has almost its full solvation shell, and it just doesn't want to go away. So what are the two mechanisms by which this kind of magnesium can go into solution. So basically it boils down to making this OH into a water molecule so that it's no longer anchoring the magnesium to the surface and then magnesium goes away. So the one possibility is that one has kind of a double proton transfer from a water molecule which is close to this magnesium, and then it basically by this double proton transfer one forms here a water molecule. One has a full solvation shell of magnesium with 6 water molecules, and we have an OH on the surface that is still there. But this would eventually lead to a completely OH-covered surface and will block the reaction. There is a second mechanism by which a water molecule, which is already present in the solvation shell, transfer its proton to the OH. And therefore, one has then a magnesium OH complex that forms, which is solvated, and this can go into solution. And by going also through the reaction, we can see that this is the kind of the magnesium 1+ that is hepatitized, which will explain the ratio between hydrogen and water. With this, I'm in the end. I hope I was able to show you that it's really, we need to take care what kind of boundary conditions we have in order to embed our small supercell into the environment in order to be able to reproduce what we see in the big system. And then I was discussing 2 examples for platinum and magnesium. In the end, I would like really to acknowledge Sudarshan, Florian, Stefan, and Jörg also in particular, and thank you for your attention.